Hi, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Today we're going to be looking at another heavily requested NileRed video on turning old jewelry into pure gold. Now, gold has a few interesting uses in nuclear technology. I'll probably talk a little bit more about those as the video goes on. Let's take a look.
A few months ago, a patron of mine contacted me because he saw one of my old videos where I separated gold from computer parts. He was wondering if I could do a video like that again, except on jewelry, and he wanted to send me some gold-covered chains and an old Rolex. He had no idea how much gold was actually in any of it, but he was pretty sure there was a decent amount. I thought it would be fun to pull out whatever was there, even if it weren't very much, but I did have one concern. Before this, I'd never tried extracting gold from jewelry, and I was a bit worried that I might mess it up. This is because with gold, even a small loss can start to add up quickly.
Yes.
For example, this here is $5 worth, and it's such a small amount that you might not be able to see it on...
Just lose it.
I really didn't know very much about the whole process, but I didn't think that I could screw it up that badly. So I had him send it all over to me, and it arrived about a week later. It was a huge mess, so I went to organize it a bit, and almost immediately, I started doubting that these were just gold-covered chains. The gold-plated stuff is usually made from a cheap metal base like copper, silver, or steel, and the density of these are about half that of gold. Most of the chains, though, were really heavy and felt way too dense to be made from any of those metals. When it was all organized, I saw that I had 5 chains, a watch face, and a bunch of scrap stuff. The first thing I did was take a look at the watch, and I noticed that it was still working. The fact that it was still functional, and that it probably didn't have much gold or any other precious metal in it anyway, I really didn't think it was worth destroying.
Yeah.
So I put this on the side and I moved on to looking at the chains. The first thing I wanted to know was the purity of gold in each of them, and to do this, I just looked for a stamp. I was able to find one on 3 of them, where 2 of them were marked as 18 karat, and the other one was marked as 14. One of the smaller ones wasn't marked though, and the clasp of this one had broken off, where it was probably written.
One misconception I had when I was younger was with carats being a unit of purity for gold, but they're a unit of size for diamonds. So that kind of confused me a little bit.
Now, because I didn't have a real idea of what these chains were made of, I had to test them. There are a lot of different ways that this test can be done, but I just used what I had on hand, which was concentrated nitric acid. So to the big chain, I made a deep scratch in it, dropped it in the acid, and left it there for a few minutes. Gold jewelry comes in different carats, and it refers to the purity of the gold. 24 karat is 100%, and everything else is based on a fraction of that. So, for example, with 18 karat gold, it means that the pure fraction is 18 over 24, or 75%. The other 25% is often made of other metals like copper, silver, or iron, which both change its color and make the gold more durable. Nitric acid is able to react
gold's
with
very
most
malleable
metals and dissolve them, but some metals like gold are really resistant. At lower carats, below around 8 or 10, the acid can eat around the gold atoms and dissolve the other metals. However, when we start getting up to 12 or 14 karat, the gold is able to block the acid. This is why, even after sitting here for a few minutes, pretty much nothing happened. A deep scratch also didn't do anything either, so together, this told me that not only was it not plated, it was probably at least around 14 karat. Now, using the same test with a...
He gave you gold that was too good, buddy.
of the smaller chain, it was a different story, and the acid immediately started attacking it. It also changed colors. It was initially blue, and then it slowly shifted to being green because of all the copper nitrate that was forming. About 10 minutes later...
Just like why the Statue of Liberty is green, because it's got all that copper. Didn't start off that way.
There was almost nothing left, and it was mostly just some light black flakes. From this, I took a small sample, and I added it to a test tube. Then I diluted it with some more water, and I added some concentrated hydrochloric acid. And almost immediately, a whole bunch of white stuff appeared, which was probably silver chloride. This told me that, well, there was silver present, and that the chain was probably just a mix of copper and silver. The last thing to look at was all this scrap, but I didn't bother testing it because none of it felt very dense at all. I just assumed that it was all less than 14 karat, and I decided to process it separately.
Did you know that gold could actually be radioactive? Gold 198, it's a beta source that emits beta particles, and it could actually be used as an effective means to treat cancer, specifically prostate cancer. Now, because with prostate cancer, you use what is called brachytherapy, so think close range therapy. So you just put the source of that gold near the prostate where the actual tumor is, and it has an effective range, those beta particles, of about 4 millimeters. But it transmits a lot of energy. Betas are electrons, so they're heavier than gamma rays, because gamma rays is just light, doesn't have any mass. So they end up doing more damage to cells at close range, which is why betas are more hazardous to be consumed, but they can be stopped with the amount of plastic that's about as thick as a credit card. So not much of an external hazard, but internal can be hazardous. But you can harness this and you can have it hit the tumor and not cause much damage to the rest of your cells. That's one of the big things with radiotherapy for cancer is it can wipe out a lot of your cells, specifically fast dividing one immune cells. And usually you're hooked up to something that's basically a big targeted X-ray or gamma ray machine, and it does like a big saturated effect on your whole body. It wipes out a lot of cells. It's effective against fast-growing cells, which, like cancer, but also your immune system. So it leaves you very weak after that treatment. But the advantage to using something like gold for prostate cancer is you don't have as many of those side effects, since it's not going to cause as much damage to your healthy tissue. So gold can actually be an effective way to cure certain forms of cancer, like prostate cancer. Now, if it's all spread it around, like stage 4 cancer would be less effective, where it's infiltrated your lymphatic system and it's just about everywhere in your body. Unfortunately, that's still a challenge that a lot of doctors struggle with, just because it's everywhere. Prostate cancer, early detection and early elimination using a targeted thing before the tumors can get too big. It can be an effective treatment.
Now, though, I put it aside and I went back to working on the chains. I now had an idea of how much gold was in each chain, and I knew that this one probably didn't have any gold at all. I decided that I would still process it though, but I would do it with all that other scrap stuff. To process these chains though, which actually had gold in them, the next step was something
14, 18,
called
that's pretty good.
This just meant that I had to mix it with another metal like copper or silver to knock down the gold concentration. Typically, the target is around 6 carats, so about 25%. By doing this, the gold stops being able to block the other metals from nitric acid, and you'll see why this is important later on.
I like that he has to essentially dilute the gold by combining it with other metals.
The most common and probably best metal to inquart with is silver, mostly because it's very easy to recover and to use in another run. However, I didn't have any silver, and this was just a one-time thing, so it made no sense for me to go out and to buy some just for this. I instead just used copper that I pulled out from a bunch of wire that I had left over after moving to my new office. I then weighed each of the chains, and based on their purity, I calculated how much copper was needed to knock it down to around that 6 carat point. For the larger one that I determined to be at least around 14 carats, I went ahead and assumed it was 18, just for the calculations. I did this because it was better to overestimate how much copper I needed than to not add enough. Now, to mix the copper with it, I had to melt it all together. I'd done this before on a very small scale in a porcelain dish, but never with this much metal. There are many different setups that people use to do this, but I wanted to go with the simplest and the cheapest. From some videos that I saw, I found that it was possible to just do it with a paint can, some blowtorches, and fiberglass insulation. So I ordered the fiberglass from Amazon, and I went and picked up the torches and the paint can from my local hardware store. Also, while I was on Amazon, I
I
picked
like that he shows his work where he's getting all the materials from. So you can attempt this if you want to.
a small metal melting starter kit. Now, to put this whole can thing together, it was really easy. I just had to cut out a small circle to cover the bottom, and then I cut a larger piece to cover the sides of the can. For the torches, I drilled a hole in each side and shoved them in. I then put a crucible that I had inside, turned on the torches, and tried to position them properly. To try to keep the heat inside, I covered the top with more fiberglass, and I waited for it to warm up.
That
As a
even
point of
heating at the
safety,
bottom.
though, some torch heads, like the one I have on the right, are made of brass. For general use, this is totally fine, but in this case, the tips of the torches are surrounded by insulation. This causes them to heat up way more than normal, and with brass, it can start releasing toxic zinc vapor. For this reason, I did it all in a fume hood, but I probably should have just avoided brass altogether. My torch head on the left is made of steel, and I could have just gotten another one. But anyway, after 15 minutes or something, it didn't even look like it was close to being red hot. I honestly wasn't very surprised by this, and I assumed it was because the can and the crucible were way too big for these small flames. The simple solution to this was to just build it using a smaller can. The one issue with this, though, was that the only crucible that I had that would fit in this was made of graphite. I wasn't sure if it was okay to use with torch flames, but I figured I'd give it a try. I did a test run, and I was able to get it red hot, and it didn't look like it was getting destroyed by the flame. So I let it cool back down to room temperature, and I started loading it up with the copper and the chains. It only had space, though, to fit one chain and its copper, so I'd have to wait for it to melt a bit before adding more. So I put this inside my little can thing, turned on the torches, and covered the top. Within just a few minutes, it already started glowing red, and to get it going faster, I blasted the top with another torch. Then I let it sit there for a little while more, and it eventually started to melt.
So what he's doing, there actually are a few thermodynamic principles at work that are used in the nuclear reactor, and that's you want the heat distribution to be even, just so everything is uniform. In a nuclear power plant, at least the pressurized water reactor that I worked at, there's a few different ways to make this sort of adjustment. And one is the initial loading of the core. You can put what's known as burnable poisons, and that is materials that, by poison we mean material that stops the fission. Materials such as boron, for instance. Boron has a higher probability of absorbing neutrons compared to uranium-235 for causing fissions. Another example for this is gadolinium. Now, what's nice about gadolinium is it's going to absorb a neutron, but then it burns out. It doesn't disappear, but gadolinium-157 in particular has a very high probability of absorbing it, but 158 doesn't. So it'll absorb it, then it'll still be there, but it doesn't have any of those properties anymore, so it burns its way out. And you can position this strategically at certain elevations of the core to keep it evenly over the course of a fuel cycle. Like, you would put it in a zone that would normally be a hot spot, it would burn itself out, but by the time it's burnt out, the rest of the core will be at that elevated temperature. Other ways to do this are with control rods, as simply, because control rods, since they go into the top of the core, when you insert control rods, not only are you lowering reactor power overall, but you're actually lowering the amount of heat, the amount of fissions that are taking place at the top of the core relative to the bottom. Compare that to adding boric acid to the reactor. That causes more of an effect to lower the amount of heat, the amount of fissions that are at the bottom of the core relative to the top. So it's important to keep in mind that it's not just power level that you are controlling in a nuclear power plant. It's what's known as radial and axial flux, which you can think of which is the technical term, which for radial, it's how much power is being produced towards the center versus towards the sides, and axial being how much power is being produced towards the top versus the bottom.
There was still a bunch of solid stuff left in it, but it was liquefying. There was now a lot of extra space, so I started adding more copper and gold. I started with the small 14-karat chain and all of its copper, and it might have looked a bit weird here. And this was because, to make sure that there was no moisture on any of the metal, I preheated it with a torch. I really blasted it a lot though, and the chain melted a bit into the copper. I waited for all this to melt, and then I added half of one of the larger chains, along with half the amount of copper. It very well might have been possible to do the whole thing.
I like how he's just throwing them in there real fast. I mean, yeah, he's using a small container because he had the challenge with the larger one, but it's just kind of funny to watch.
It didn't really make much sense to try. There was still a third chain to do, which definitely wouldn't have fit, and it made no sense to risk overflowing it if I had to do a second run anyway. But in any case, with everything added, I covered the top again, and I waited for it all to melt. When it eventually all liquefied, I stirred it around really well to make sure that all the metals were evenly mixed. After that, I covered the top and I heated it for another few minutes just to make sure that it was nice and hot, and then I poured it all into a can full of water.
That's a satisfying sound.
When that was done, I dropped the crucible back in, and I set up the second run. Just to make things go faster, and to make sure that there was no moisture in it, I gave all the copper and the gold chains a strong preheating. Then, I slowly added everything to the crucible. At first, I just did this with the tongs, but I found that doing this for all the copper would take forever, so I just started pouring it in from a vial. It was a lot faster to do it like this, but it wasn't nearly as accurate, so I ended up missing with a bunch of the copper. However, this really wasn't much of an issue, because not including just a small amount of copper wasn't going to make much of a difference. When it all eventually melted, I mixed it around like before, and I let it sit for a few more minutes. I then went to pour it all into the same can, but I was a bit surprised because liquid metal started coming out from the side of it before the front. This definitely wasn't a good thing, but for the time being, it was still a bit too hot for me to investigate. So for the time being, I put the crucible back in the can, and I turned off the torches, and I let it cool. When I took a look at it a few hours later, I noticed that there were some huge holes in the side of it, which were made by the torch flame. This is why you aren't supposed to use oxidizing torch flames on graphite for long periods of time. I was lucky it didn't end up being a problem, but it could have caused the crucible to break when I tried picking it up. This could have not only caused all the gold to spill everywhere, it also would have been a huge safety hazard.
Yes.
But anyway, getting back now to what was thankfully not a catastrophic failure.
No burnings.
All my gold alloy was now in this can. So I just quickly got rid of all the
mushrooms.
water, and this was what it was like.
Hard
By
mushrooms.
dumping all the liquid metal directly into water, it created these pieces that have relatively high surface area. Ideally, though, they would have been a bit flatter and looked more like cornflakes, but I think I just didn't pour it from high enough. In the can, just sitting on the fiberglass, I also found this chunk of alloy which had leaked out the side of the crucible. So I took this, along with all the flakes, and I put them in a beaker. Then, on top of all of this, I poured in some dilute nitric acid. A reaction immediately started, and some nasty nitrogen dioxide vapors started coming off. The nitric acid was attacking all the copper that I just inquarted it with, as well as any other metals that might have been mixed in with the gold. In this case, the other major metal that was used was probably just silver.
That is quick.
There might have been small amounts of other metals though, like nickel, zinc, or iron. The nitric acid converted the copper metal to copper nitrate, which, like I mentioned before, has this really nice blue color. As the concentration of the copper nitrate increased though, it slowly shifted to being a dark green. The silver and other trace metals are also being converted to nitrate salts and getting dissolved into solution. The silver nitrate is colorless though, and there isn't enough of the other metals to really affect the color. When the reaction died down, I added another load of dilute nitric acid, and it started bubbling like crazy again. I waited for this to also settle down, and when it was done, I dumped everything into a larger beaker. I then kept adding more of the dilute acid, and I continued the same cycle. As I mentioned before, I'm using dilute acid here instead of the concentrated stuff, and there were two major reasons for this. The first one is that it stops the reaction from getting out of control, and the second one is that I needed the extra water to dissolve all of the metal salts that I was making here. A major effect of this, though, is that compared to the concentrated stuff, the reaction is slowed down quite a bit, which makes it take a lot longer. So to speed things up, this reaction needs to be heated, usually close to the boiling point. I didn't use a thermometer, though, and I thought I was close enough.
Again, one of the advantages of nuclear power over, say, coal is you don't deal with this kind of stuff. There's no NOx and SOx, as they say, nitric oxide or sulfur dioxide. Those are the real nasty, poisonous greenhouse gases. I know a lot of people talk about carbon emissions, which nuclear doesn't have either, but this is the real nasty stuff you don't want up in the atmosphere.
But I don't think I was. And because of this, it would initially react quite a bit when I added more acid, but then it would kind of just stop. However, just by looking at the stuff at the bottom, I could tell there was still a lot of copper left. At the time, I thought that maybe the acid was just depleted, so I dumped off the liquid and I added new fresh stuff. The same thing happened again though, so I started getting suspicious. But still, I decided to dump everything off and to add more fresh acid again. This also eventually stagnated, so I dumped in even more, but it didn't seem to do too much. It was only at this moment that I realized I probably wasn't heating it enough, so I cranked my hot plate to maximum, and the difference was pretty obvious.
Whoa.
I let this react for another hour, and it got rid of pretty much all of the copper. Just to really make sure that it was all gone though, I boiled it one last time with more nitric acid, except this time it was a bit more concentrated. When it was done, about 40 minutes later, I dumped it all off. What I had now was this really soft gold sponge, but it was still contaminated with a lot of the dissolved metals. To get rid of them though, it was quite easy, and I just had to wash it with boiling distilled water. I did it 3 times in total, and after the third one, it was still a bit blue.
It kind of looks like that stuff that you see as like sunken treasure on like old Spanish galleons or something that you see at the bottom of oceans, and then people recover it. It looks like this dirty stuff, but when you clean it up, it turns out to be gold, which is pretty cool.
But that was okay. Now that pretty much all the other metals were gone, I added concentrated hydrochloric acid. I brought this to a boil, and then I started adding small amounts of concentrated nitric acid. On their own, neither of these acids are able to dissolve gold, but together they make something called Aquaregia, which is actually able to.
Never heard of that.
They work together, where the nitric acid starts by oxidizing an extremely small
pause at this. Yeah. That's cool.
amount of the gold to make gold 3+ ions. This reaction is really unfavorable though, and almost immediately after they're made, they revert back to being metallic gold. With the hydrochloric acid present though, it can attack
anything with 3+, that's a super strong positive charge that don't want to stay there for long.
the gold 3+ ions and convert them to chloroauric acid. This breaks the equilibrium between the gold and the nitric
Say that 10 times real fast.
acid, and the gold ions are continually fed forward to make the chloroauric acid. I kept adding nitric acid until it pretty much looked like all the gold was gone, and then I left it overnight. The next day, I still had some solid stuff at the bottom, but it wasn't gold. It was all just silver chloride, because apparently there was still some silver left in the gold. So moving on, I diluted.
He brings up silver. Silver is actually used a fair bit in nuclear plants as well. In fact, the control rods at the plant that I used weren't boron. Boron's pretty commonly used term for control rods, but they were silver, indium, cadmium. And the nice things about those control rods is that particular alloy is very, very strong, very resistant to the extreme amount of temperatures and pressures that are in a pressurized water reactor. So we're talking 2235 psi and upwards of 590 degrees Fahrenheit. So a lot, much higher compared to, say, a boiling water reactor, which is still pretty high. Boiling water reactor, which is still very high, but we're talking 1,000 to 1,100 range. So not nearly as high, but those, also have variable neutron capture things, so they can go through a wide range of neutrons. That particular type of silver, indium, cadmium poison to slow down the neutron reaction. It's got that little extra versatility and can make a very effective means of slowing down a fission reaction, and of course shutting down the emergency shutdown, the classic reactor trip where you press a big red button or turn a big red switch and all the rods fall in about a couple of seconds. We actually test that every refueling outage before we start up the reactor again to make sure that function works. Rod drop testing is very interesting.
It with an equal amount of water. This is done just to knock out any silver chloride that might still be dissolved. Then on top of this, I added some concentrated sulfuric acid to knock out any lead that might be present. When refining jewelry, there usually isn't any lead to begin with, but this was just a precautionary measure.
Okay.
As far as I could tell though, nothing happened because there was no lead. I let this stir for about
trying to think of where he would get it
and
from.
then I filtered it off. This was done by just using a couple coffee filters.
Oh, so look at that.
Passed through was really nice and clear. When it was done, I washed the filter paper with a lot of distilled water because as long as it was yellow, it meant that there was gold in it. When I eventually had a completely colorless filter paper, I took away the funnel and I dumped all of this gold solution into a larger container.
One other thing that radioactive gold is used for is for tracing fluids, for instance. Gold 198 has a half-life of about 2.5 days, which is short enough that it goes away in a reasonable amount of time, but long enough that it's a stable beta emitter, and betas are very good at tracking and tracing the amount of flow in pipes. That's very commonly used in the oil and gas industry. So it's interesting that nuclear kind of helps out oil and gas in that particular way.
I also washed the beaker a few times with distilled water to make sure that I transferred everything. Okay, so now the next step was to get the gold out of this solution, and to do this, I used potassium metabisulfite. I made a solution of it by adding about 120 grams to 200 mils of distilled water. I thought this was enough to dissolve everything, but it wasn't, so I just kept adding more water until it all disappeared. Normally, I would have just dumped in all of the metabisulfite, but I thought that maybe it could be interesting to add it dropwise. The moment I did, some brown gold powder started precipitating out, but it wasn't particularly interesting. So I ended up just scrapping that whole idea and dumping in the rest of it. The potassium metabisulfite is a reducing agent, and it reduces the gold in the chloroauric acid back to its uncharged metallic form. It also reacts with leftover nitric acid though, which is why it was important to use a minimal amount of it when I was dissolving the gold. Other metal salts, like those with copper or iron, won't be reduced by this, and this whole step was to help further purify the gold. As one point of safety though, this reaction releases quite a bit of sulfur dioxide gas, which is dangerous to breathe.
That's the other one, huh? He had NOx earlier, and now he's got SOx. So we're going the full spectrum here.
Personally, really sensitive to it, and even very small amounts can trigger some asthma symptoms. So for this reason, it's extremely important to do it in a well-ventilated area, and I did it in my fume hood.
I do like him mentioning the safety aspect of these experiments and telling what type of PPE, using the fume hood, showing what examples he uses. That's all very good.
I then let it sit for a couple hours to fully react, and for all the gold to settle down to the bottom. This was what I had a few hours later, and I dumped off all the water. All of the gold was then transferred to another beaker with the help of a bunch of distilled water. This was all brought to a boil, and after heating it for a couple minutes, I dumped off the water. This washing step was then repeated 4 more times using boiling distilled water. At this point, the gold is usually pure enough, but I wanted to get it as pure as I possibly could. So I decided to do another washing step, except this time with boiling hydrochloric acid. When the concentrated acid was added, it became yellow because an extremely small amount of gold was able to dissolve. The amount, like I said though, was extremely small, and it was nothing worth worrying about. This was brought to a boil, and I repeated the same thing 4 times, and each time, the solution became more and more colorless. After the last one with the acid, I did it 2 more times with boiling distilled water. Now, just as a quick comparison, if we look at the gold before the acid and afterwards, it's quite different. The color of it is a lot lighter, and apparently, this indicates a higher purity. I poured off as much of the water as I could, and then I put it back on the hot plate to dry it. When most of the water was gone, I mixed it around a bit, and I let it sit on the hot plate for another several minutes. I also occasionally stirred it, and eventually, I was left with a really dry powder. This was more gold than I had ever held in my life, and when I weighed it, it came out to be about 75 grams. Based on the carats of the chains, I expected to get about 77.9 grams out, so this was extremely close. This estimation was based on the assumption that that unknown chain was 18 carats though, but it probably wasn't. Also, the amount of gold in the other chains was probably slightly less than the carats they were marked with. Now the next thing to process was all that other scrap. I didn't include this with the main batch because I wasn't sure what was in it, so I wanted to process it separately.
Now, one other gold application, nuclear application, is a little dark. If you haven't seen my video talking about different types of nuclear explosions and nuclear weapons, I'll pin that in the comments for more context here. But gold can be used in the so-called salted nuke as an application for that. Cobalt is the more commonly one term. You've probably heard of cobalt-60 radioisotope used associated with that sort of weapon. So the idea behind a salted nuke is you're trying to make it have fallout that lasts a very, very long time, because most of it, the fallout gets blown out within a couple of weeks or so. But this one, you're designing it to have a lot of fallout and a lot of contamination, hence the term salted, like you're salting the earth, which is what they did in ancient times to really destroy a country, essentially. You can use gold 197, which is just natural gold. That's the stable isotope, as a little jacket in your thermonuclear bomb. So yeah, putting gold in your nuke is exactly what this would be. And during the fission reaction that occurs, it's going to absorb neutrons, and you're going to have a bunch of gold 198 that is going to be left over. Now, it does have a half-life of 2.5 days, so it can stay around for a bit longer to add to that initial amount of radioisotopes. But even if you were one of those crazy people that likes, one, making nuclear weapons in general, and two, making the fallout be as deadly as possible, you're better off with cobalt because of its longer half-life. Again, we're just talking 2.5 days, so it's going to make that first week even more hazardous. But yeah, it wouldn't do the same as cobalt. This has never actually been tested, by the way, with gold. This is purely speculative. Gold could conceivably be used in that way, but salted nukes in general, I think they're kind of overrated. Again, I talk about it more in that other video, but they're also mainly because they're so unreliable in that fallout, the main thing that determines how deadly the fallout is which way the wind's blowing after the attack. So you don't have as much control compared to, say, a conventional nuclear bomb, as weird as that sounds, but one that you just focus on an airburst, maximize destructive power to whichever target you're going for. That's a bit more controllable by the person using it, whereas the fallout is probably a lesser concern because the area is already destroyed anyway. And if you're looking to maximize contamination, you're actually gonna reduce the effects of the explosion because you're gonna want to go for a surface burst. It's still gonna be devastating and it's still gonna be horrific, but not to the same level as an airburst and we're talking a weapon that's designed to wipe out populated areas, that sort of thing. But yeah, you could potentially use gold instead of cobalt if you really wanted to. But Enough about that topic. Just wanted to point out that using gold in nuclear applications could have a dark side, just like any other piece of technology, really. But I much prefer the idea of using it to treat cancer.
It all seemed to be plated or low-carat gold though, so there was no point in quarting. I just jumped right to adding the nitric acid, and like before, there was a big initial reaction, but it quickly died down. I then added the liquid from the test that I did earlier on the piece of that small chain. I also added the full chain itself.
Now it's
that
blue.
was most likely just copper and silver. This was all boiled for a couple hours, and when it stopped reacting, I figured it was done.
Green now.
I poured everything off,
This is just
and
funny.
I washed the stuff at the bottom a few times with distilled water. It looked like almost everything had dissolved, except for some of the stuff that was completely plated with gold. Then just like before, I poured in hydrochloric acid, waited for it to boil, and added small amounts of nitric acid. Eventually,
Whoa.
almost everything had disappeared, but the solution was green here and not yellow because there was still a bunch of copper.
Yeah.
I let this cool overnight, and in the morning, I poured in a bunch of water. Then I mixed it around, and I also added some sulfuric acid. After this, I let it sit for about an hour, and then I filtered it. It was the exact same setup as before, just with a funnel
Now it's
and
green.
a few coffee filters. It was eventually all done, and now the next step was to see how much gold was actually in there. So now to this, I added a solution of potassium metabisulfite until all of the gold had precipitated. Then I mixed it around, and I let it sit for a few hours. When I came back, I poured off all the water, and it was way more gold than I expected. I really didn't think I was going to get much of anything out of it, but this was a pretty decent amount. I now had to clean it up a bit, and I did the exact same thing as before, where I started with water washings, then I did some acid ones, and finished with some more water ones. I dried it on my hot plate until it was a nice and crispy gold powder, and then I weighed it.
Crispy.
Like I said before, I really didn't expect to get much out of this, and I was really surprised that it was almost 6.5 grams. All of this was then combined with my other gold powder, and my total now was 81.6 grams.
Wow.
At about $42 a
Good thing he did that process again. He was able to get a good bit more gold out of that. That's fascinating.
gram USD, this is close to $3,400.
There you go.
Or about 4,500 Canadian. This was way more than I ever imagined I'd be extracting from my patron, considering when he first pitched it, he just said it was some gold-plated stuff. However, I was really happy it turned out this way, because it made the project a lot more fun. But in any case, the last thing that I had to do now was to melt all of this powder down into a solid chunk. To do this, it was pretty simple, and the first thing that I needed was that small porcelain dish that I got in that kit from Amazon. Then I picked up some borax from my local hardware store, and I also got out my torch. This dish had never been used before, so I had to give it a glaze. This was done by first getting it really hot, and then sprinkling small amounts of borax onto it. The major purpose of this was just to prevent the gold from sticking to the dish. When I felt that I had done a decent job, I started adding the gold. I was a bit concerned that the torch might blow the powder away, so I swapped it for the less intense one. The gold was dense enough though that this didn't really seem to be much of an issue, so I ended up going back to the other one. The gold started melting relatively quickly,
here we go.
and I just kept topping it up with more powder and occasionally with some more borax. When I was eventually done, I was left with this giant blob of gold. I let it cool for a few minutes so that it would solidify, and then I knocked it out of the dish. I dunked it in some water to cool it down quickly, and I also washed it a bit to get rid of any borax residue. The final result was this giant chunk of gold with a mass of 81.31 grams. This was a bit less than the powder that I started with, but that was probably because the powder still had a bit of water or moisture left in it.
Sure.
As I mentioned before, this was more gold than I'd ever held before, and because it was so dense, it also felt abnormally heavy. Now that I had this huge piece of gold, I wanted to do some tests on it. I had always heard that gold was really malleable and soft compared to other metals, and I wanted to see for myself. I did try bending it with just my fingers, but it was absolutely impossible, so I moved on to using
shake,
tools.
not a whole lot of give.
The first thing that I tried was to push on it with a steel spike, and I was kind of able to stab it in.
Making some
With a
holes.
hammer, though, I was able to smash it all the way through. And when I took it out, I had
Check
this
that
nice
out.
little hole in it. The next test was to smash it with a hammer and see if it would flatten. Gold is definitely malleable enough to do it with the right tools, but doing it like this just isn't going to work very well. The only result that I really got was a bunch of hammer marks in it, and it didn't get much flatter. Now the last test was to see if I could cut it with a pair of pliers. With some soft metals,
okay.
this is easy to do, but the gold was relatively tough. I was able to pull some very small pieces off, but that was about it. I did find it funny though, because even though these pieces were really small, it was still something like $10 to $20 worth of gold. From these few tests, I saw that the gold was definitely malleable,
That's funny.
but it wasn't nearly as much as I thought. It's still enough though, that making something out of pure gold might not be the best idea. With jewelry, things like rings and
You see in all these video games that like the super armor or what have you is like all this gold plated thing, or like these big, fantasy shows, like the big golden sword, but probably not the best idea of all time. Also, it'd be really expensive.
chains would definitely deform over time and potentially break. This problem is fixed, though, by mixing it with other metals like copper, silver, or iron, which greatly increase its durability. But anyway, the piece now was all mangled, and I just couldn't leave it like that. I wanted to fix it up, and I thought that it would be cool to make some small gold bars. So I put everything
Nice.
back into my dish, and I started melting it. And at the same time, I heated the
There you
graphite
go.
mold that I got with that kit on
Little
Amazon.
mold.
When it was all liquid again, I picked up the dish and I carefully poured in some of the gold.
I like that you see this sort of thing with torch and pliers, and the guy's probably wearing some level of PPE. I heard a lot of people thought that's what I was getting into when I was going to be a nuclear engineer. Like I'd be doing that with some green glowy thing of uranium. Probably saw it on some episode of The Simpsons, but no, never done anything like this or seen. You don't see this at a nuclear plant. It's just funny.
Then I took out the
Look
bar
at
by just
that.
flipping the mold upside down, and I moved on to making another one.
Just slides right out.
And after that, the last bit of gold was just enough to fill one of the smaller ones. I quickly knocked out this one as well, and I cooled them all underwater, and this was my final result. They were of course really far from being perfect,
Just
but I
throws them.
still liked how they turned out. From all the nitric acid waste, I was also able to recover some silver,
A bar of
and I made
silver.
another little bar with it.
Nice.
I didn't feel like it fit in this video, but if you're interested in seeing how I got the silver out and dealt with all the waste in general, I've put together another video. This one, though, isn't posted on my main channel here, and can be found on my other one called Nile Blue, and there's a link in the description. As one final thing after all this, I went to a company called Kitco, and I had them test the purity of both the gold and the silver. They initially told me that they were both 100%, but they didn't know that I wanted a printout of the results. So I had them run it again, but this time, the results were slightly different. The silver was still 100%, but it said that the gold was 99% and the rest was tungsten. However,
Tungsten.
I think this was just an error, because if I got out 100% of the copper and silver, there's no way there would still
How'd
randomly
you get
be
tungsten?
1% of tungsten in there.
Yeah.
When I posted this to Patreon a few days ago, one of my patrons, Victor, gave a good explanation as to why it might have told me there was tungsten. The gold was tested by something called X-ray fluorescence, or just XRF, and he said that sometimes it can get confused between gold and tungsten.
Okay.
This is because with XRF, the tungsten and gold peaks are very similar. Another patron found these two XRF results for tungsten and gold, and you can see how
So where this sort of thing comes from is every element has their own characteristic energy associated with that. And it's an X-ray that just comes off it, and that has to do with just its atomic shape what orbitals we're talking about and how those electrons essentially play. Here you have just these little X-ray signatures that are consistent with gold, and apparently gold and tungsten happen to have that similar characteristic, which is fascinating. I've also done spectroscopy. This was in labs when I was in college for different sort of where the peaks were from gamma rays. You'll see them on charts that look just like this. That'll tell you the energy level associated with that. Here we're talking the energy is going to be on the order of keV, or thousands of electron volts. Gammas are going to be considerably higher scale, on the order of several hundred keV to MeV, or millions of electron volts, which makes sense because gammas are higher energy than X.
The peaks slightly overlap. Victor also told me that I didn't even need to encode for this video, and there's another method that can be done where the jewelry is directly treated with the Aquaregia. This method would not only save a lot of precious nitric acid, it also might be a lot faster, and it has way less copper waste. But anyway, in conclusion, I was able to extract the gold, and I didn't totally screw it up. The only sad part now
Nice.
is that I don't get to keep the gold, and I have to send it all back to my patron. But either way, him sending it to me in general was still really nice.
That's something, yeah. Hey, you basically... Enriched isn't the right word, because enriched would imply that he made the gold radioactive, but he refined the gold and upgraded it to nearly pure gold, and then sent it back from a whole bunch of stuff when the guy initially thought it was just gold plate, that would give you next to nothing. That's funny.
And, well, trusting. So a big thanks goes out to him for that. If any of you guys are interested in just donating your gold to me, though, I'm definitely open to it.
That was so cool. I liked seeing that whole process, all the different types of acids and precipitates he uses, and all those intermediate steps where this stuff looked nothing like gold at all, and yet he clearly had a plan, a procedure, and a mindset of how he wanted to get from point A to point B, and it was really fascinating to follow along. And I was just thinking, how is he gonna turn this into gold bars? Because I know that's what the title of the video says, and there you go. He got it. That was really fun to watch, and also really fun as a little reminder of the nuclear applications of gold. And it's the first time I talked about spectroscopy at all on my channel at all, and that really takes me back. I had to dust off a few cobwebs there. Thank you very much for watching. I'll see you next time.